Okay, we've seen before that if we start from there, then you get your displacement equation as x equals a sine omega t. Now, that's not usually the case. I mean, if you were to get a spring going in SHM, then you would actually pull it down first and release it from a stretched position to get it bouncing. So in other words, on the reference circle, you'd actually be starting down there. So what we're going to do, we'll start at a different position and see what happens. So if we start in the vertical position and move around, then we'll get a graph that looks like this for displacement time. And so looking at that, that means we must get, for displacement, a cos omega t. And then you can go from the other. So x equals a cos omega t. Differentiating that, you must get velocity equals negative a omega sine omega t. And acceleration equals a omega squared cos omega t. Now if you actually started at a certain angle, so let's say we started here at phi, so it started early, so let's say you then go around, so you're rotating around this way, you're going to head up and then go around like that. This is your displacement time. And this shows that we have our normal formula, a sine omega t. The angle is just that little bit more, so there's phi attached to that angle there, and it just increases that angle from the start. And now if we look at these, two SHMs in time like that are in phase. If they're like this, then essentially they're out of phase. So in class you guys are going to derive some formulas for the horizontal mass and spring, vertical mass and spring, and the pendulum. Pendulum, if you remember, we did an AS. We did the formula, so the first practical, and there'll be one that's t equals 2 pi square root something over something.